A short discussion right now regarding the lab. So if there are no other questions, then I'm going to run through some of the tests. What did we look at last time? We looked at silver, and does somebody have their flow chart handy? Yeah, if I can just borrow it for a second. This one? Yeah. Thank you. All right, so we looked at silver and iron. The next ion is the aluminum 3+. So if our unknown contains some aluminum and we react it with HCl, there should be no reaction. And so the equation for this is Al3+. Chloride's not going to precipitate anything. We get NR. And then we take this CCS from 1 and then add the ammonium buffer. And from this we should get a white and a gelatinous PPT. And the equation for this reaction is this. Gives us the aluminum hydroxide solid plus 3 ammonium. Then we subject this to PPT, which is kind of white or colorless, to excess sodium hydroxide. So 3, we'll take the PPT from number 2 plus hydroxide. And what this does is it dissolves the PPT, and we end up with a CCS. You know, the solution might not be colored, but that's what we should get with aluminum. So the reaction here is that the aluminum hydroxide gets attacked by hydroxide as a ligand, and we form a complex, which is tetrahydroxyaluminate 3. And so the tetrahydroxyaluminate 3, does that react with hydrogen peroxide? So we'll see that in the next step here. We'll take our CCS from part 3 and react this with hydrogen peroxide. And the aluminum in the CCS part 3, we should have no reaction. I mean, can you oxidize the aluminum further? I mean, it's already plus 3, so is it possible to oxidize it to plus 4, let's say, or plus 5? No. And so here we're going to get no reaction as well. And then what do? We heat to remove the hydrogen peroxide, but I'll show that in a different step. I'll show that after we actually use it. And so the HCl comes next. And what the HCl does is it destroys the complex. That is, we get this CCS plus the HCl, we're just going to get another CCS. And so the tetrahydroxyaluminate plus 4H plus is going to give us Al3 plus 4 waters. And so pretty much we're going to destroy the hydroxyl ligands, and then we're going to convert the hydroxyl complex into an aqua complex. So the HCl. And then we add some ammonia in the next step. So this will be number 6. We take the CCS from 5, add ammonia to form a white PPT, or colorless PPT. This is just a gelatinous PPT. And that is, the aluminum ions are going to precipitate out with hydroxide generated from the hydrolysis of ammonia. Form this plus 3 ammoniums. Okay. Then in the next step, we dissolve this precipitate with HCl. So step 7, the PPT from step 6 plus HCl should yield a CCS. So that's just the aluminum hydroxide being attacked by acid. I'll just write the net ionic for this. 3H plus is going to give us Al3 plus 3 water. This is a metathesis or acid-base type reaction. All right, and then finally, in the last step of this, we take the CCS from part 7 and then add ammonia to this in the presence of aluminon. We don't have to write out the formula for aluminon. Aluminon is just this dye that's going to get incorporated into the crystal lattice and give the white precipitate a color. And so we get the red lake. The red lake is a red PPT. And the red PPT, what is it made out of? The red PPT is just made out of aluminum hydroxide that's been colored with aluminon. Aluminon gets incorporated as an impurity. So there's not much aluminon in there. And so what we do is we represent that as an impurity by maybe putting it like a double dagger like this next to the aluminum hydroxide to indicate that it's not pure. And then 3 ammoniums. So we go through all these steps and then we come out with positive, for the Al3 plus ion. And so this would be the this would be the test for aluminum. Okay, then we had the test for chromium next. So let's take a look at that. This is chromium 3. So, for chromium 3, if our original unknown contained chromium 3 and we add HCl, what do we get? NR, no reaction, because chromium 3 plus chloride, we don't expect any precipitate. There's no driving force for that. There's no driving force for reacting with H plus either. And so nothing happens. 2. Now, is this a CCS? What is a CCS? CCS stands for clear colorless solution. And so is chromium 3 colorless? Pale yellow, chromium 3? No, it isn't. It's not pale yellow. Who knows what the color of chromium 3 is? Well, kind of a blue. Well, we'll just call it CS, clear solution. There's going to be some color to it. So the CS from 1 is next subjected to ammonia and ammonium. And we get a precipitate. What color is the precipitate?
Yellow.
No. No. Just look at your flow chart. It's all on the flow chart. Gray-green. Get a gray-green precipitate. Okay, what is the identity of that precipitate? Well, chromium 3 is going to react with the ammonia and water to produce chromium 3 hydroxide, solid, plus 3 ammonium. Yes, we have some ammoniums, which is going to push the equilibrium to the left, but for the most part, we'll precipitate out a lot of chromium 3, the bulk of it. It's highly insoluble because of the 3 plus charge. Okay, in the next step, we're going to add excess hydroxide to this. And so we take the precipitate from step 2 plus excess hydroxide, and what do we get? NR. And so here, chromium 3 hydroxide, unlike aluminum, it doesn't pick up another hydroxyl ligand. It doesn't want it. Aluminum does. All right, then after the excess hydroxide, we hit it with hydrogen peroxide. So let's go to the next step here. And so does chromium 3 react chromium 3 hydroxide react with hydrogen peroxide. So if we take the precipitate from step 3, reacted with hydrogen peroxide, yes, it does react. And we get a clear, do you know what color it is? Now you could say it. Yes, clear yellow. Clear yellow solution, CYS. All right, so the reaction here is this. It's a redox reaction. Hydrogen peroxide is our oxidizer. And so we're going to oxidize chromium 3 to what? So we're going to convert chromium 3 plus to chromate. Is that right? Yeah. You should be able to confirm this on your flowchart. And then hydrogen peroxide gets converted into something else. We don't really care because hydrogens and oxygens always balance out at the end. And so here, let's go ahead and balance this, right? 1 chromium, 4 oxygens. We'll need plus 4 waters. That gives us 8 hydrogens, so we'll need 8 H pluses over here. Is that right? Okay, 8. And then, maybe I messed this up this morning. So, could have messed this up. This looks different. And so I have 3 plus, and what is this? Plus 6. 3 plus 6 means plus 3 electrons, right? And so that looks to be it. And so we'll get chromium 3 plus 4 H2O. Liquids goes to chromate plus 8 H plus 3 electrons. All right, this is not your standard half reaction that you'll find in the redox chart. However, this is one of your standard ones that you find in the redox chart. If we don't have the redox chart available, we can balance it quite easily nonetheless. We'll need 2 waters. It's like, that gives us 2 hydrogens, 4 hydrogens, so we'll need 2 hydrogens over here. And then the charge is plus 2, so we'll need 2 electrons here. So the other half reaction will be hydrogen peroxide plus 2H plus 2 electrons yields 2 waters. Okay, now let's add up the 2 half reactions, being careful to make sure that the electrons balance. 3 electrons here, 2 electrons here. And so I'll multiply the first one by 2. So that gives me 2, 8, 2, 16, 6. And I'll multiply the second one by 3. 3, 6, 6, 6. And then I'll add both reactions, half reactions together, which will give me 2 chromium 3 plus 8 H2O liquid plus 3 hydrogen peroxide plus 6 H plus. The 6 electrons will cancel, so I'm going to leave those out. This is going to go to 2 chromates plus 16 H plus 6 H2O liquid. All right, let's simplify this here. 6 H2O liquids will cancel out 6 of these, leaving us 2. And then I have 6 H pluses. That'll give me 10 H plus over here. So let's clean this up. This is going to give me 2 chromium 3s plus 2 waters plus 3 hydrogen peroxide yields 2 chromates plus 10 H plus actually that's it. Let's just double check that it's balanced. We look for atom balance and charge balance. So I got 2 chromiums, 4 hydrogens plus 6 is 10 hydrogens, 2 oxygens plus 6 is 8 oxygens, 2 times 4 is 8 oxygens. So the atoms are balanced. Let's check the charge. It's plus 6 over here, minus 4 plus 10 gives us plus 6. And so this is balanced here. So this looks to be the redox reaction to convert chromium 3 to chromate. Okay, once we have chromate, then we're going to heat to remove excess hydrogen peroxide. Okay, let's go ahead and heat to remove the excess hydrogen peroxide next. we don't want excess hydrogen peroxide in there because that could oxidize things we don't want oxidized. And so here, heating the hydrogen peroxide, delta is the symbol for heat, just decomposes into H2O liquid plus oxygen gas. And now we add HCl to the solution 3,4. So 6, we'll do solution, actually 4,5. Solution 4,5 plus HCl yields what? What happened to our chromate when we add HCl to this? It goes from a clear yellow solution to a clear COS. What does that mean? Clear orange solution. So how does that happen? Well, the addition of HCl to chromate converts it into what? Chromate converts into dichromate. I'm just following along the chart. You know, if you're having trouble following me, just look at the chart and it tells you what it forms. Chromate goes to dichromate. Although I have your chart. You have it written down somewhere? You don't? All right, here. I don't want to take it. I thought if you had it written down in your notebook, you know, you should have it written down in your notebook because it's much quicker than reading through this and trying to figure it out. Well, you know, dichromate is 2 chromates minus a. Dichromate is 2 chromates minus a oxygen, and so oxide is not stable, but you know, 2 H pluses will stabilize that by forming H2O liquid. And so here we can convert chromate into dichromate. What kind of reaction is this? Not a redox reaction, because the oxidation states don't change. So if it's not a redox, what is it? Acid-base. Exactly. This is an acid-base reaction. And interestingly, acidic solutions favor dichromate, and it turns out that basic solutions actually favor chromate. And so what's the next step? To add ammonia. And so step 7, we're going to take the solution from 6 plus ammonia, and what does that do? No precipitate. Actually, maybe I need. I don't want to take too much time, so this is why. This is why I want to go through the flow chart myself. Actually, we're 94. Thank you. Okay. So we add ammonia, and what does it convert it to? We go from a orange solution back to a yellow solution. And that's because the ammonia does this. The ammonia attacks the acid to form ammonium. And so the more ammonia we add, the less acid we are going to have, and then we're going to have a shift left. Le Chatelier's principle. And so basically, this is pH dependent, the color. In acidic solutions, it's orange. In basic solutions, it's yellow, and you can change the color. In fact, you can go back and forth between yellow and orange just by adding acid or adding base. So after we add the ammonia, then we're going to add some barium chloride. So here we'll take the solution from 7 plus barium chloride will yield a yellow PPT. And so the reaction here is that the barium ions like to precipitate out with chromate ions to form yellow barium chromate solid. Barium chromate is kind of a faint yellow. Depends on, but it could be brighter in shade. So this is a positive test for barium ions, or is it? Is it a positive test for barium? No, this is the positive test for chromate. Chromate. Or maybe it was the positive test for dichromate? Or was it? No, this is a positive test for chromium 3+, not chromate. All right, the next ion is zinc, is that correct? So Zn2+, let's take a look at that here. So if our unknown solution contains zinc 2+ and we react it with HCl, we expect no reaction here. And that is Zn2+ plus chloride won't precipitate. NR1, 2. Now we're going to take our solution from 1 and add ammonium to this, to C. But we end up with NR here. Although we expect a reaction because zinc 2+ should precipitate with ammonia and ammonium to form zinc hydroxide. This reaction should have happened, but it didn't. Why? Why didn't it? Well, the reason it didn't is because we kept the ammonium concentration fairly high. And this fairly high ammonium concentration means we shift this to the left to prevent precipitation. And so we had no precipitation because we're shifting this backwards. We should have gotten a precipitate. Should have gotten a precipitate, but didn't. And so we're using Le Chatelet's principle, to prevent it, or this whole thing about the buffer we were talking about last time. Okay, next. Three. After we add the ammonium, then we're going to add excess hydroxide to this. And so we're going to take the solution from 2 plus excess hydroxide, and here, what do we get? Oops, no, sorry. We don't add excess hydroxide. We add we take the solution from 2 and add ammonium oxalate to this, and we get no reaction. And that is Zn2+ will not react with oxalate or ammonium ions, NR. Here. Either ammonium or oxalate. Okay, then we evaporate to remove the ammonium. And so that's the next step here. Evaporate to remove ammonium. We don't want any excess ammonium here because there's potential interferences from ammonia. And so here, how do we remove it? Well, if we have ammonium ions and chloride ions present, we can form ammonia gas and HCl gas here. If you look at this reaction, the driving force is in the reverse direction. This is a strong acid, HCl, going to a weaker acid, ammonia. And so there's really no driving force in the forward direction. And so the only thing that's driving this reaction forward is this, gas formation. Because we are going from a weaker acid to a stronger acid here. All right, what's next? Adding sodium hydroxide. And so if we take the solution 3,4 and add sodium hydroxide, we get a white precipitate. And that is Zn2 plus 2 hydroxides is going to yield ZnOH2 solid. That's an insoluble hydroxide. That's why we expected it to precipitate out earlier, since it is forming an insoluble hydroxide. Okay, then, oops. That is if we add just the right amount. But in this case, we need to add an excess. And so what we'll do is initially we're going to form this white precipitate. But this white precipitate can be attacked by 2 more hydroxides. And when it's attacked by 2 more hydroxides, we form this complex. Tetrahydroxo zincate 2 ion, which is a CCS. And so the white precipitate gets converted into a CCS here. And so add a little bit of hydroxide, we get a precipitate. Add a lot of hydroxide, that precipitate should dissolve to form the hydroxo complex. And then we go on to the next step. Step 6. And we have potassium hexacyanoferrate. And so we'll take the solution from 5 plus potassium hexacyanoferrate K4, and this is going to yield a precipitate, a gray-blue precipitate. Plus HCl. And so what is the purpose of the HCl? To make the solution more acidic. And so typically what happens is if we have hydroxyl ligands on here, sometimes these are pretty strongly bonded to it. And so one way to destroy this complex is to add acid. That'll eat up the ligand here. And so we'll end up with 3 zinc ions, what we call those, and 4 H2O liquids here. All right, then from this, we take the free zinc ions and then precipitate it out with that anion. And so when we precipitate it out with this anion, this is the hexacyanoferrate. What's the charge on hexacyanoferrate? It's 4 minus, it's ferrate 2. And so we expect this precipitate to form Zn2 FeCN6. That looks like a typical, what kind of reaction? What type of reaction is this? This is a metathesis reaction. Some people hate that word metathesis. They criticize it and they say, why don't you just call it double replacement? You know, we've been dealing with double replacement reactions all this time. Just call it a double replacement reaction, right? Don't use these flowery words for something so simple, right? Well, it turns out this isn't what forms. what forms is this. We need 2 zincs plus 2 potassiums plus 2, is that right? No, 3 zincs, sorry. 3 zincs plus 2 potassiums plus 2 FeCN6, 4 minuses. And we're going to precipitate out this, Zn3, K2, FeCN6 solid. And so this is why I like the term metathesis, because metathesis are ion combinations. And it doesn't have to be an AB plus CD pattern. This is what we call a mixed cation salt. This is the gray-blue precipitate. This mixed cation salt, mixed cation salts aren't that rare. In fact, you saw mixed cation salt in Chem 1A, maybe. Did you ever see this species? Fe3O4. Have you ever seen that? What's the charge on iron? What's the charge on oxygen? -2. The charge on iron would be 8/3, right, yeah. The charge on iron is 8/3, which is 2 and 2/3? 2 and 2/3. But what is iron 2 and 2/3? Is that the iron and 2 and 2/3 cation?
It's a mix of
No.
iron 2 and iron 3.
It's a mix of iron 2 and iron 3. We have 2 iron 3s and 1 iron 2. This is called magnetite. And it's a mixed cation salt, or mixed cation ionic compound. Maybe I should call it that. All right, so this is the positive test for zinc. Okay, let's move on. I want to complete all of these. The next is nickel. So let's take a look at nickel. All right, if we have nickel in our unknown, and we add HCl, we expect an NR. That is, nickel 2 plus will not precipitate out with chloride. 1. And then we take our solution. What color is nickel?
Green?
Yeah, all right, good. CGS, you're the first person to say correctly. CGS from 1 plus ammonia and ammonium, the next step, yields what? NR. And so nickel should precipitate with ammonia, but it doesn't. We expect to form nickel 2 hydroxide. Nickel 2 hydroxide is an insoluble solid, should precipitate out. Well, what's preventing it from precipitating out? The high concentration of ammonium, or relatively high. You don't have to have a super high concentration. But we just bump up this concentration, shift this way, and this prevents nickel from precipitating, as long as we have enough ammonium in there to prevent it. All right, then from that we go to oxalate. And so 3, let's write it up here. Number 3, we take our CGS from 2 plus ammonium oxalate yields NR. It turns out nickel 2 plus and oxalate aren't going to precipitate. And so we get NR. here. Nickel 2 plus and ammonium aren't going to react either. Next, actually I should do that because ammonium, we always have to worry about ammonium because you know what ammonium is? Usually you don't think of cations being attracted to cations, right? But ammonium is a special cation because ammonium is a pretty good reducing agent. That's why in one of the earlier steps, you know, we have to get rid of the hydrogen peroxide. Otherwise, the hydrogen peroxide will attack ammonia or ammonium and convert that. All right, so we got that. Now we have to get rid of the ammonium. So in step 4, we're going to evaporate the ammonium. Well, how do you evaporate ammonium? Usually you evaporate the water and you're left with ammonium salts, right? And so technically it's not really evaporating, it's decomposing the ammonium. And so how do we decompose the ammonium? Well, if there's chloride present, did I already do this? Yeah? No. If there's chloride present, then we should be able to form ammonia gas and HCl gas. We drive these off as gases. There's a gas formation here. If there's nitrate present, which there should be some nitrate present from the unknowns, ammonium and nitrate, or you add it, will form some nitrous oxide and H2O gas. So we'll need 2 of those. This is a redox reaction here. Gas formation is not a driving force for redox reactions, but it can help. This is not a redox. Here. All right. So we evaporate the ammonium, and then we add some sodium hydroxide to this, excess sodium hydroxide. And so we go with the CGS from 3,4. So it's going to be 5. Plus excess sodium hydroxide yields precipitate. Do you know what color the precipitate is? Blue? And just read it from the flow chart. What color is the precipitate? No, you guys are in the wrong place. You've gotten lost in the jungle of words here. No, green, that's it, green precipitate. So nickel 2 plus 2 hydroxide yields nickel hydroxide. I gotta go fast because I don't want to waste too much time talking today. So 6. After we get this nickel 2 hydroxide, what are we going to add to it? Ammonia. And we got this green precipitate. Now to the precipitate in 5, we add ammonia to this, and what happens? We end up with a pale violet.
Yes.
Yes, pale violet. That's right. So clear violet solution. And so what happened here? What happens here is the precipitate disappears. We got 6 ammonias, and we're going to form the hexaamine nickel ion, which is pale violet in color. And so, in other words, we dissolve the precipitate. So what's a positive test result for nickel? A positive test result for nickel is you get a green precipitate that dissolves. And so, well, let's look at this. This green precipitate is pretty characteristic of this nickel nickel. And so what is a negative? Now, that's unusual, you know. A lot of people don't talk about negative test results, but what would a negative test result for nickel be from here? A negative test result, quote unquote, is where we take the green precipitate and make it disappear. That is, we take the green precipitate and dissolve it until there's no more green precipitate left. And so in the previous test, the positive observation for nickel was the green precipitate form. If you want to negate that, then you get rid of the green precipitate. And so that would be what they call the negative test.
So if you get rid of the green precipitate, what color does it turn? Just clear or
Pale violet.
pale violet?
Pale violet solution, right? But you're left, at this point, you're left with a white precipitate and a green precipitate. You remove the green precipitate, you're going to be left with the white precipitate. The white precipitate is the magnesium, which we haven't talked about, magnesium hydroxide. Normally I go with magnesium first, but your book, I don't know why it didn't do that way. But that's all right. All right, now what we're going to do in step 7 is we're going to take this CVS and add DMG, dimethylgloxine, and we're going to get a precipitate. What color is this precipitate? Red. And so we should get a red precipitate here, and the reaction here would be the hexamine. I guess DMG is good enough that we don't have to destroy this complex with acid. This one just leave as is, and then react it with DMG ion, which is going to be C4H7N2O2. C4H7N2O2 with a charge of 1-. So we'll need 2 of those to form Ni, and then 2 of these C4H7N2O2 solid. And so that's our red PBT. So this would be the positive test for nickel 2 in our original unknown. All right, let's go on to the next ion, which is going to be magnesium ion. And so for magnesium 2+, if our original unknown contains magnesium 2+, then we don't expect anything to happen with HCl, NR. That is, magnesium 2+ will not precipitate out with chloride. Let's go on to the next one. In the next step, we reacted with ammonium, and so we'll take the solution. What kind of solution is it? Well, this should be a CCF with magnesium, and we're going to add ammonium, and we get NR. However, we do expect magnesium to precipitate. You know, magnesium forms an insoluble hydroxide, and so if we take magnesium 2+ plus 2 ammonias and 2 waters, this should have precipitated to form magnesium hydroxide, solid, plus 2 ammoniums. But again, utilizing Le Chatelier's, or the common ion effect, we're going to prevent this from precipitating. And so, prevent from precipitating. And so what that does is it just leaves it in aqueous phase, and then we can go to the next step, which is adding ammonium oxalate. Oops. Okay. Yeah, you know, the book, reverse the order, but 3. If I take the solution from 2 and add ammonium oxalate, then nothing happens. NR. Magnesium doesn't react with ammonium or oxalate. In fact, you'd expect it to react with oxalate and precipitate, but it doesn't precipitate. So magnesium does not precipitate out with oxalate, or undergo any kind of redox with ammonium or oxalate. All right, then we add, well, we evaporate to get rid of the ammonium. So for evaporate ammonium off, or decompose, actually we should say decompose the ammonium off. And then we're going to add sodium hydroxide, excess. So we'll take the solution from 3,4 plus excess sodium hydroxide. And what do we get from this? A white PPT. Good. Following along. So white precipitate. And so the reaction here is Mg2 plus. Now we'll react with a hydroxide, form magnesium hydroxide, an insoluble precipitate, which should have formed over here but didn't because we're controlling it. To this white precipitate, we're adding ammonia now. So let's see what happens here. So in 6, we'll have the precipitate from 5 plus ammonia yields NR. Nothing should happen here. The magnesium hydroxide is not going to form a amine complex. NR. Why? Think about that. 7. We go from the white precipitate with HCl. And so we'll take the precipitate from 6 plus HCl, and we should get a CCS, clear color solution. And that is the magnesium hydroxide, solid, should dissolve in HCl to form Mg2 plus 2 waters. Okay, in the next step, we're going to add magnesium reagent and sodium hydroxide. And so we destroy the precipitate. Now we're going to reform it, but we're going to reform it with magnesium reagent. And so here we'll take the solution from 6 plus sodium hydroxide plus magnesium reagent yields the
Magnesium hydroxide.
what color is it?
Blue.
Blue
Purple.
lake, right? Gelatinous precipitate, the blue lake. So what is the reaction here? The reaction here is magnesium 2 plus 2 hydroxides. Now the magnesium reagent is like the aluminon. You know, it's just a dye to color the precipitate. And it's a very selective dye. That is, it binds to the magnesium. And so what we end up forming is magnesium hydroxide, which has been, contaminated by this dye, so now it's blue rather than white. And so this is the positive test for magnesium 2 plus. I went out of order, but it's okay. All right. Now calcium. If our original unknown aqueous contained calcium and we add HCl, do you expect anything to happen? No. That's what we see in our. And calcium and chloride aren't going to precipitate. All right. 2, the solution from 1, which is a CCS, right, plus ammonia and ammonium yields NR. Calcium hydroxide is soluble, so this one we wouldn't expect to precipitate anyway. There's no driving force. NR. 3. We'll take the solution from 2 and then add ammonium oxalate. And we get a white PPT. And that is calcium ions like oxalate. And when calcium and oxalate combine, we form calcium oxalate, which precipitates. Whereas magnesium doesn't. oddly enough, because magnesium is even smaller than calcium, so you expect it, but I guess it just doesn't fit right in the lattice. So we get this calcium oxalate, and then we do what with it? Yeah, the HCl is going to do what to the precipitate?
Break it down.
Good. And so we get the precipitate from 3 plus HCl, and we end up with a CCS. Clear color solution. All right, and so the reaction here is just another metathesis or an acid-base reaction where we take the calcium oxalate, solid, plus, we'll need 2 H pluses from the HCl, form calcium ions and 2 oxalic acids. So we're going from stronger acid to weaker acid, driving this reaction forward. And then finally, we'll take the solution from this and put it in the flame. So the solution from 4 into the flame should give us a red flame. And so the reaction for this is we have calcium 2 plus AQ. We can vaporize that in the flame to the gaseous state. Now, the flame is the 4th state of matter. You know what the 4th state of matter is? A plasma. A plasma happens when you have a very high energy gas. A high energy gas is a high temperature gas. High temperature gas has lots of kinetic energy. Lots of kinetic energy means there's violent collisions. Violent collisions means there's ions and electrons in the flame. And so, you know, there are parts of the flame that are electron rich that will reduce the calcium to calcium metal. And so the calcium 2 plus picks up electrons from the flame to go to calcium. And then calcium atoms can collide with each other and get excited. This either represents an impurity or could represent what we call an excited state of calcium. This would be an electronically excited state. And it doesn't stay there forever. It's going to drop back down to the ground state and emit an H nu. What's an H nu or multiple H nus called? Depending on what excited states, you know, but each, you know, one calcium atom can only emit one H nu. Anybody remember what H nu is? Chem 1A? The name of it? No. No. Nu is frequency. H is Planck's constant. H nu is?
Energy.
H nu is energy, but we give it a name. A photon. Yeah, good. A photon of you know, some color or colors. All right. So this you should get the brick red. This would be positive for calcium ions here, and then 2 more ions. So we have the sodium ion test. You know, where we take an unknown and just put it straight into the flame. Sodium is incredibly sensitive, so you should get a very intense yellow flame. If you get a very dim yellow flame, you might think maybe it's contaminated. You know, we've been having some contamination issues. People have been telling me that there are people in this lab with very sloppy technique maybe that are contaminating various solutions with their droppers. So be careful, because, you know, contamination will yield the yellow flame. And it's easy. You can contaminate it with your fingers. For example, if you spend all this time cleaning that platinum, and then don't touch it when it's hot, otherwise you'll get burned. But if you let it cool down and you touch it with your fingers, you're going to spend another 30 minutes cleaning the sodium you just left from your fingers off that platinum wire. And so the yellow flame here, we know we have sodium ions present in solution, and you only need minute quantities. Here, calcium is very insensitive. You know, that is, you need large quantities to really see that. But here, no problem seeing this. We vaporize the sodium ions into the gaseous state, and then reduce those to sodium metals and atoms in the gaseous state, then excite those, and then let those drop back down to the ground state and emit photon. So that's the sodium ion test. And then the last one we had was the ammonium ion test. If your unknown contains ammonium, and then we add some sodium hydroxide to this, and then we generate a CCG, a clear colorless gas. The clear colorless gas we test with litmus, and we end up with blue litmus. And so in this particular, yes, we could heat this to get more CCG, but if we take ammonium and hydroxide, we're going to form ammonia and water. If we heat this, then we can drive off the ammonia as gas. And then the ammonia driven off as a gas can come into contact with litmus paper. Red litmus paper is the acidic form. We call it H-lit. Lit because the anion is so long. It's just an acid. It's a colored acid. And the conjugates are different colors. So H-lit is red. And then this accepts a proton, so we form ammonium, which is colorless. And we form LiT minus. LiT minus, the conjugate base, is blue. So that's how our indicator works here. You just go from the red form to the blue form of the litmus. All right, any questions for this? Uh-huh. I can't answer that. You know, this is the unknown. You're supposed to be independent totally. That which brings me to this. Normally I just grade this straight off the unknown. You know, you either get it right or you get it wrong. But normally for some people, their unknown doesn't go so well, and they lose huge amounts of points. And so to prevent you from losing huge amounts of points, we're going to have is a two-part report for this. It's not going to be a formal report. The first part's very simple. You just tell me what cations you tested positive for. That's it. You tested positive for this. And then the second part of the report, I want you to turn all these in. You know, just write them out. You don't have to type them out. Just write them out by hand and include those in the report. The observations and the equations for each ion. Okay, and then I can give you points for that, and then I'll give you points for your unknown.
So for all 10, not just the ones we got in the unknown.
Yeah, right. Not for all 10. Yeah, basically all 10, but it should be very easy, right? We just did it, and it didn't take very long. But this repetition of seeing it, hopefully you'll understand more of the chemistry that's happening. Okay.